right? So this is example 3.6.6. You have the sequence of function is following, right? And we want to show that this does not converge uniformly to it does not converge uniformly to 0 as n tends to infinity, right? Okay, so how do we show this, right? The first thing is if you can make some sketches, right? This is your x, so this x is over 0 or more. So let's look at this function here. If your n is equal to 1, then this would be x over x plus 1, right? So as your x increases, it will actually x is 0, so it will be 0. So it will go like this, right? It's increasing, but it will, in the limit, it will go to 1, yeah? As your x goes to infinity, okay? But we are actually not interested in x going to infinity, okay? We're interested in n going to infinity, right? So when your x is equal to 2, so it will be x over x plus 2. So this one will be somewhat lower. Okay, so it will still go towards 1, right? So you can see that as you add your n, right? As your n increases, because your denominator is actually increasing, right? So its value on the y-axis will actually decrease, okay? But still, in the limit, it will still tend to 1 as x tends to infinity, okay? But we're not interested in x going to infinity. We're interested in n goes to 1, to 2. So we're interested in n going to infinity, right? So you can imagine that the curves are actually going to be flatter and flatter, right? Like this. Okay. Now, so if it actually converges uniformly to 0, we will have something like this. So bounded by epsilon, right? Okay. Which means if you have, so let's sketch the bound. So you have some bound like this. So this is plus epsilon, this is minus epsilon, right? So it's bounded within epsilon, right? Now, so what happens is that you can see that it's actually not possible for it to become bounded because, okay, so you will see that the boundedness then depends on x, right? Whereas you cannot have dependence on x for uniform convergence. So you can see that, for example, this n, it should be maybe something like 10 already, right? So you can see that for your x values that are lower than this particular cutoff, is bounded, right? Because the red line here, the difference from 0, is actually bounded by the blue line, yeah? But outside of this particular x value, it's not bounded, right? You can see that the red line is, the difference is already exceeding the epsilon, right? The point is that you can't find such, you cannot find such an n, so there is no n, okay, such that when your index exceeds this n, right, you will have this condition being true, that there is no such n, right? you can see that all of them will violate. Even if you make your n very large, at most it will be flat like this, but towards the end it will still keep on increasing, yeah, because your n ultimately is actually a constant here, right? Once you fix it, when your x surpasses your n, it will start growing, right? So it will definitely exceed. It will definitely go outside of your epsilon sooner or later. Okay, so you don't have uniform convergence in this situation, right? So this is the intuitive argument that you can give by a using a graphical argument, right? If you want to argue it in a more rigorous way, so if you look at the notes there, the example, all right. So you first note that the following, yeah. So we first note that this is bounded from above by the supremum, right? Okay. Definitely, right? Because this is definitely bounded by the supremum. Okay. Now, x over x plus n is definitely bounded by 1, yeah? No matter what is your n is a constant, right? So it's definitely bounded by 1 over x, yeah? So your supremum over x, right? Therefore, it's very clear that your sup, right? Your supremum is equal to 1, right? Actually, from this curve itself, you know that the sup is 1, yeah? Because very obviously, the curve does not exceed this line of 1, right? This function, right? Okay, so this function of 1 constant here can be your sup, okay? Can be used as a sup. So, and therefore, you will see that this thing here, all right? So this is your Fn. You subtract the limit that is supposed to go to, let's say 0, right? So this is basically just bounded by 1, right? The sup. So it cannot be bounded. So this, if you compare it with this condition, right? It means that it's only bounded when your epsilon is greater than or equals to 1. If you choose, because this is a very clear bound already, okay? So your values cannot exceed 1. So if you choose epsilon to be 1, okay? That means you choose this blue line, right? This blue line you put here. So definitely it will be okay, yeah? Because any of these differences from your f, okay, the limit is definitely less than 1. All right, you choose 2 is also okay, right? So anything that is only okay for epsilon that is 1 or more, right? If you take more, is also okay, yeah? Because if it's if your bound is 2, then definitely they are all, the difference is all bounded by 2. Then the problem comes when you choose any epsilon that is less than 1, okay? Like for example, you cut like this. You cut like this, definitely this condition will not be satisfied, because over here you will have some value of n, whereby this difference, right, will actually exceed your epsilon. Okay. All right. So then you show that there is no uniform convergence, because for uniform convergence to occur, it has to be true for all epsilons, yeah, greater than 0. But here you show that it is only true, that inequality is only true when your epsilon is over or equal to 1. Okay. All right. So is it clear? Example 3.6.6, how you actually approach such problems. Okay, is it okay with this example?
Yes, doctor.
Okay, anyway, like I said, when you study certain problems and you find that sometimes the analytical argument is a bit hard to follow, generally, if you make some sketches, things will become clearer, yeah? Okay. But then, of course, the sketches are not proofs, yeah, but they just help you get the argument right. Okay, then you have theorem 3.6.1. This is an important property of uniform convergence. Why we study uniform convergence is because the following, yeah. So theorem 3.6.1 says is basically a result saying that if you have a sequence of Riemann integrable functions, right? And they are uniformly convergent, then your limit, right, your fx, which is the limit of the sequence of Riemann integrable functions, is also integrable. Okay, which basically it has this integrable means the integral exists lah. Huh? Okay, if you say fx is integrable, you're basically saying that means that usually you will say integrable over certain let's say some set like this, some interval like this. So you're basically saying that this is okay. It's actually not infinity. Okay, it has some value, right? So basically, if this is uniformly convergent, yeah, and the integral exists. Okay, let's say AB. Then this implies that the integral also exists. And is given by this interesting result, which is you take the limit, okay, is equal to right. So this is an important result. Okay, you have some integral. You're interested in an integral where this function here is actually dependent on n, yeah. If you let n goes to infinity, what will happen to this integral? Now, it seems like if you have not studied some calculus, it seems like a lot of people will just move the limit sign inside here and then do the calculation, right? This will generally give you answers that are either right or wrong, depending on whether your fn here is uniformly convergent. If it is uniformly convergent, this operation will definitely be okay. If it is not uniformly convergent, then if you do this operation, it is an illegal operation. But sometimes if you are lucky, you will get the correct answer, even though you use an illegal operation, right? But that's just being lucky. All right. So I give you some examples there. All right. Example 3.6.7, right? Three point 6.7. So you have this function, okay, and it has been shown to be uniformly convergent, yeah, to 0 when for x greater than or equals to 0. Okay, this means that if you make some integral like this, okay, so this is uniformly convergent, right? So therefore you can move the limit sign inside, okay, and then you can evaluate this limit here, which is basically 0, right? So you integrate this, okay. Now take note that this function here is Riemann integrable, yeah. Integral fn x dx. So let's say over 0, 1 is integrable, right? How do we know that? So basically this function here is you need to find some kind of a bound for this function. How could you show that this is integrable? Of course, you can actually directly evaluate it. Yeah, you can directly evaluate this function, and if it is evaluable, then it is integrable. Okay. Okay, I'll come to the integrable part later. So since you have you move the limit inside here and it is equal to 0, therefore this integral is equal to 0. Yeah. Okay. Then I have a remark here. If you don't have any concept of uniform convergence, right, when you are faced with this sort of limit, right, of this integral, you would have to do this integral first and then only take limit. All right, which means you will have to do, so if you take this integral, so this is equal to the following. Because this is you look at this part, right? This is basically the derivative of x squared plus n squared 1 over 2, right? Okay, so it can be seen as a form like this: f prime x, g prime x and gx, right? This integral. If you integrate a ratio of the derivative to itself, this will give you the log function. Okay. Let's see. Sorry. Yeah. Then you evaluate it like this. Okay. So definitely this is integrable, right? Because this is it integrates to a log plus n. Okay. Evaluate it at 0, 1, so you will get 1 over 2 log 1 plus 1 over n squared. Right, so basically this is 1 over 2 log of x squared plus 1 minus, sorry, n squared, yeah? N squared plus 1, then minus log of n squared, so which is 1 over 2 log of n squared plus 1 over n squared, right? So you can cancel this, okay? So you get this part. And definitely if you take limit, when n goes very large, this will be close to log 1. So this will go to 0, okay? All right. So, but then of course you, depending on the particular form of this function, sometimes it is very difficult to evaluate this integral, or actually impossible to evaluate it. So I mean, like, it's impossible to evaluate it analytically. So you will find that it is very difficult to find this limit if you do not know the concept of uniform convergence. At least if you know what uniform convergence is, you can check whether this function is uniformly convergent. And if it is uniformly convergent, then just feel free to move the limit sign into the integration operation. All right, that will make things much easier. Okay. Okay, I think I have a duplicate. I have a duplicated example 3.6.8. So you just ignore that. Yeah. I'll correct that later. Then you look at example 3.6.9. Okay, so here you have x over x n, not uniformly convergent. Okay, and we know that this is not uniformly convergent because of simply because I think this is the same situation just now, right? Just now that situation like this. Okay. Okay, and it's not uniformly convergent because for any arbitrary cutoff epsilon, so this is your 0, right? You can always find some function where this part will actually exceed. So you can always find something that exceeds epsilon, right? So not uniformly convergent. So in this case, when you want to find this limit, you cannot write it like this. Because x over x plus n is not uniformly convergent. Okay. Suppose you ignore that. Suppose you just go ahead and you do it anyway, right? Okay. If you do it anyway, of course you will get equals to 0. Do anyway. You will get 0. Okay. Now let's compare the answer with doing it the right way, right? If you don't have uniform convergence, then you will just try to push it through by evaluating the integral first, right? So you evaluate this integral. Okay. This integral is given by the following. Okay, this is some I think year 1 calculus material. Okay, so you can check that if you take the derivative on this part, you will actually recover x over x plus n. Okay, so this is correct, and if you evaluate this integral, it will give you something like this: 1 plus n log n minus n log of n plus 1. Okay. Right. So basically, this is 1 plus n log of n over n plus 1. Okay. So if you take limit here, then of course you will take limit here, right? And when you take limit here, you will notice something that allows you to apply L'Hopital's rule. So this will, so basically what you do is you move this n to be the denominator, so you will have log of n like this, okay? So if your n goes to infinity, this will go to 0, right? Okay, this will go to 0. And this part here, your n will go to 1, so log of 1 will go to 0. So you have a case of 0 over 0, so which means you can apply L'Hopital's rule. All right. By the way, this is the name of a person. Yeah, it's called L'Hopital. Okay, it's not L Hospital. Some students will write L Hospital. It's not a hospital. Okay, it's a French name. It's called L'Hopital. Okay. All right. So once this is in the form where you can apply L'Hopital's rule, so you will basically just take limit, right? So this is equal to so you take limit on the numerator and denominator. So you'll take derivative, right? So differentiate with respect to 1 over n, so you get minus 1 over n squared. You differentiate this guy here, you will get so you separate out to log n minus log n plus 1. So that will give you this. Okay. So then you can simplify this and you take the limit, it will be equal to 0. So in this case, it is just being lucky that this answer obtained from the correct operation is equal to the answer that you got from short-circuiting this operation, right? This is just being lucky, all right? So you should not, in general, you should not expect that if the function is not uniformly convergent, you should not expect that short-circuiting this operation will give you the correct answer. It probably won't, but sometimes you might be lucky. Okay. All right. And then finally, so these are basically the why we study uniform convergence. Is for us to finally being able to use this particular result, which will be useful later when you study distribution functions. Okay, in the distribution functions, you want to study convergence. So you might want to take the limit of distribution functions, sequence of distribution functions, right? Then your distribution function just behaves like your usual function. And if it is uniformly convergent, when you take the limit, we can actually interchange the limit and the integral operation, yeah? Because your distribution function, right, is frequently written as the following. It's some kind of integral, yeah? Okay. So if you want to take the limit, so this Fn, yeah? If you want to take limit of Fn, so it's the same as finding yourself in the situation where you're asking yourself whether, how are you going to evaluate this integral, right? And that's where the uniform convergence comes in, okay? Okay, finally for theorem 3.6.2, these are other properties of uniformly convergent sequence of functions. So you have property 1, which is if the function is uniformly convergent, then it also is pointwise convergent, right? So pointwise convergence is actually implied by uniform convergence, but not the other way around. Okay. So number 2, continuity. Yeah. If your f and x is continuous, then in the limit, yeah, your fx is also continuous. Yeah, its limit is so continuity is preserved under uniform convergence. Then number 3, boundedness. Yeah, boundedness is also preserved by uniform convergence. Okay, if your f and x is bounded, your fx is also bounded on the same interval. All right, okay. So this concludes our section on the preliminary analysis results that we will use later, yeah, for studying probability measure space. Okay, so let's take a quick 5-minute stretch, and then when we come back, we will start something that's new for you, which is they're talking about some abstract space, yeah, the probability measure space. Okay, so we'll take a 5-minute break for now. Okay, so we want to talk about a probability measure space, right? Before we talk about how to measure things in this space, we want to first define this space, right? What is this space actually? Okay, because and we want to make sure that the objects in this space have some desired property, yeah, before we actually go and measure them, right? So for this hour, these are the things that we're going to talk about. Okay, so you are all familiar with this notation, right? So this is the sample space, right? So it's just basically all particular, all possible outcomes, okay, from certain experiment. It can be a real experiment or a thought or a thought experiment, right? Like for example, tossing a coin. All right, tossing a die, right? 6-sided die. So if you toss a coin, a 2-sided coin, then your omega is, if you toss it once, it's head or tail, right? This is once. If you toss twice, so your omega will be head, tail, head, and tail, right? So you can also toss many times, okay? So we'll toss different times, your omega is different, yeah? Okay, it just basically describes all possible outcomes, right? If you have a 6-sided die, so your omega will be 1, 2, 3, 4, 5, 6, right? If you toss it twice, so basically, then you will have basically you have a 2-dimensional table, right? 1, 2, 3 until 6. 1, 2, 3 until 6. So these are all the combinations, okay? So you will have 1, 1, 1, 2, right, to describe this row, and then you have 2, 1, 2, 2 to describe the second row, and so on, right? Until the last one is 6, 6. Okay. So these are examples of the sample space. Okay, so everyone clear about that?
Yes, Doctor.
Okay, now we want to consider something that you may not have thought about before. We want to consider a collection of subsets of omega. Okay, let me clear this. So so to do this, we go to example, the example 4.0.1. Okay, so suppose you have omega equals to 1, 2, 3. All right, collection of subsets of, so what are subsets of omega? So we can form subsets by taking any kind of combinations, right? So for example, 1 is a subset of omega, right? 2, 3 is also a subset, right? Because 2, 3 is inside 1, 2, 3. Okay, this is a larger set. all right, and so on. So we want to form a collection of subsets of omega. So generally, this will be denoted by a script notation. Yeah, let's say A. So if you write A is in the usual Roman letter, sorry, this is just basically a Latin character. So in the usual way, this is basically just a set notation. If you want to indicate a collection of sets, you will write something like this, a script. Right? So the A is written like this. The B is something like this. Okay. And later you will see that the F, the field, is written like this. Okay. So for a collection of subsets, for example, if you are only interested in the singletons, right? Singletons means only a single number. So I can collect them together like this, right? So this is one example of a collection of subsets. I can also make another collection. Maybe I put 1, 2, right? This time, collection of pairs. So pairs, I can have 1, 2, 1, 3, and 2, 3, right? Okay. And the smallest possible collection of subsets will be the empty set, right? Okay, and the largest possible collection will be the power set. The power set basically consists of all possible collections of subsets. Okay, so for example, in this case, you will see that the power set is given by what is inside the text there. In this case, it will be, you think of it like this. So a collection of your subsets, right, can contain so these are the number of elements, okay, in the subset. It can contain no elements, okay, 1 element, 2 elements, and 3 elements, right, at most, because you got 3 elements, okay. So this set here will correspond to your empty set, and you take all elements, it's basically just your omega, right? So 1 and 2, you will have the following, right? Okay, so these are all here, and 2 elements, these are all here. Okay, so basically, because you are, and how many combinations are there? So this will be basically 3 choose 2. This is basically 3 choose 1. Okay, so the total number of possible combinations is equal to the sum of n choose I from 0 to n, yeah. Okay, because the number of elements here is 1, n choose 0. This n choose 1. Sorry, this is n. Your n is 3. 3 choose 2, and this 3 choose 3. Okay. So I claim that if you, in general, if you sum all of them, right, the number of elements, this is equal to 2 power of n. So your power set contains 2 power of n elements. Yeah. This comes from your binomial theorem. Okay. How does it go? So for your binomial theorem, you know that a plus b raised to the power of n is equal to the sum ni a power of I b n minus I, okay, from 0 to n. So you just take a equals to b equals to 1. So your left hand side will be 2 power of n, and your right hand side will be basically just the sum. Okay. So this is considered elementary discrete mathematics result. Yeah. Okay. So far so good. Okay. So we have the idea of a collection of subsets, right, of omega. So and then once we know this, we need to define the notion of a field. This field is actually a kind of a space, yeah, where if you perform some operations on elements in this in this field, their outcomes will still stay in the same field. All right, they won't go outside. For example, one basic example is this. To think about it, so you know that our usual operation, right? Plus minus multiplication and division, right? Of real numbers, they stay in the space of real numbers, right? They don't go outside. Okay, for example, you have A is a real number, B is a real number. If you perform an operation of plus here, it's still staying in real numbers. Same with if you subtract or you multiply or you divide. They will still stay in the same space, yeah? They won't go outside of the space. So for sample space, right, we have a notion of a field. So this field acts in a similar manner, right? It's a well-defined space where when you perform set operations on elements in this space, the outcome still stays in this space. It won't go elsewhere. So this is very important, right? Because if the outcome goes outside of this field, then we don't know what is going on. Okay, so we must first construct this field very carefully to make sure that any operation, any set operation that you perform on elements in this field, it will just end up in the same field. Okay. So the definition of the field, yeah. So actually rather simple. So the definition of a field. Okay. So you have a collection of subsets of omega. Okay. That satisfies this following three conditions. In a nutshell, 1, 2, and 3. So first one is that the collection of subsets of omega. So I'll denote by the F, okay, the script F. The first thing is your omega must be inside this field. Okay, so your field is basically a collection of subsets with three particular properties. This one, and then A in F implies that its complement is also in F. Right? This is what we call closure under complementation. Okay, so you have if you have some set that is inside the field, then it means that its complement is also inside the field. All right, it doesn't go outside. Okay, in plain language, we say this as a closure under complementation. Yeah, it doesn't go out of it doesn't go outside of the field when you do complementation. And if you have two sets that are in F, it implies that their union is also in F. So this is what we call a closure under finite union. Okay. All right, very simple, yeah. It has these three properties, all right. So then let's look at some examples. Okay, before that, other elementary facts. Theorem 4.0.1 gives you some additional facts. That means after you define a field as such, then other set operations can also give you elements that are also in the same field. All right. So I'll skip theorem 4.0.1 a bit and go to the description below. Right. Property 3 of 4.0.1 implies closure under finite intersection. So it turns out that this implies closure under finite intersection. Okay, you don't have to check the other, so you only need to check these three conditions. 1, 2, 3 to show that a particular collection of subsets of omega is a field. Okay, because in fact 2 and 3 actually they collectively will imply closure under finite intersection. What does this mean? It means if AB is in F, then it implies that its intersection is also in F, right? This is actually implied by 2 and 3. Okay, so how can we show this? Let me clear this. So it goes like this. So the logic is like this. We want to show that AB in F implies that A and B is also in F, right? Okay, so first step, 1, AB in F means that its complement, right, are also in F. Okay, so this is property 2. And then step 2, so AC, since this is in F, this implies that their complement, sorry, the union is also in F, right? This is property 3. Okay. And then, since this is in F, it implies that its complement is also in F. This is property 2. Right? So you cycle through application of the property 2 and 3. But once you apply the De Morgan's law, right, you can see that by De Morgan's law, you can check back the notes on De Morgan's law, yeah? And by De Morgan's law, so this will be equal to A intersect B, yeah? So this statement is equivalent to this statement, right? So you manage to find, start from here, you manage to show through a sequence of intermediate steps that finally it implies this, okay? All right, so therefore we have this closure under finite union implies closure under finite intersection, and vice versa, okay? You can also show the other way around, okay? Closure under finite intersection also implies the other way around. So there is both sides, right? Okay. And let's look at an example to make it concrete. Yeah. So you have example 4.0.2, right? So here's an example. Okay. First, let's look at this collection. Okay, this is not a field. Why? So first thing, omega is not an element of A, right? Okay, to be a field, the sample space omega must be inside that particular collection of subsets, right? So it's actually not inside A, right? So it's not a field. So therefore, let's add some things to it, right? So now we add something to it. So when we add, right, we add omega and its complement together. So this is a field. All right. How do we know this is a field? So we check property 1, 2, and 3, right? So property 1, omega in F, yes, right? Here. Property 2, A in F implies its complement is in F. Okay, let's check. So you check one. You have to check one by one, yeah. So let's look at the empty set, right? Suppose your empty set is your A. Is its complement in? So its complement is here, right? Okay, so it's correct. So it satisfies property 2. So how about 0? 0, its complement is 1, 2, right? Okay, you take 0, you complement it is 1, 2, right? So it's also inside A. So that's okay. 1, 2, you complement, it becomes 0, and omega, you complement, it becomes the empty set, right? So property 2 is satisfied. Okay, it has to be satisfied for all members, yeah? Okay, and then we check property 3. AB in F implies that its finite union is also in F, right? So let's look at the pairs. So let's look at this pair. So we have to check all pairs. So empty set union 0 is 0 itself, so it's inside, right? So in fact, actually, the first part of checking is trivial because the empty set union, anything is empty set union, some non-empty set is the non-empty set itself. So this part is actually trivial, yeah. Checking this part is actually trivial, right? So you see that it's actually inside, inside, and inside. Okay. Then you look at the pair here. 0 union 1, 2 will give you omega, right? So it's inside A. So you can also do so then you union that. So 1, 2 union the omega, you get omega, right? The larger set, right? Okay. So I think that's about it, right? 1, 2, 3. So 1, 2, 3, 2, 3. Okay, 0. So you can also do 0 with omega. That definitely gives you omega, right? So definitely this is also correct. Okay, and therefore we confirm that A is a field. Right? Okay, you don't have to check property 3 prime, which is closure under finite intersection, because it's equivalent to property 3. Yeah, so you only check property 1, 2, 3 is enough. But sometimes it may be easier to check closure under intersection. Okay, so depending on situation, yeah. So it's good to know that these two properties imply each other. Okay, in this case, it's easier to, well, actually in this case, checking property 3 or 3 prime is about the same ease, yeah. So an example there is given. Okay. Now, maybe I can ask you some other. Can you give me some other examples of fields? Okay, or maybe I ask you whether this is a field. So this is C. So is this a field? Anybody wants to answer? Is C a field? Anyone?
It's not a field, Doctor.
Yeah, why?
Because if we look on the second property, let's say we take the A is equal to the 1, there's no complement inside the C.
Okay, correct. So this is not a field because the complement of 1, right, is not inside this collection of subsets, okay? So it's not a field because you take its complement is outside of it, you see? So in order for it to be a field, we have to make sure that its complement is inside, right? So that will be 0, 2. So this is a field. All right? You can check that this is also a field that it satisfies these 3 conditions. Okay. Then definitely the power set, right? The power set is always a field. Always a field. So the power set here, you can check that there are 2 power 3. There will be 8 elements. Yeah. You can verify yourself that it is actually a field. Okay. And then maybe a final question here for this question. Give the smallest possible field. What's the smallest possible field that you can construct? So as you can see, there are many different fields. Yeah, given an omega, you can make many different fields. Okay. So in this case, the largest field that you can get is equal to the power set, right? How about the smallest one?
Is it the null and omega set?
Yeah, that's correct. So if you just take, you basically just take the following. Okay, so this is definitely a field. This is what we call a trivial field. There's no other interesting sets inside it except the empty set and omega itself. You can see that it definitely satisfies the first property. Definitely satisfies property 2. In this case, so this guy is complement is omega, and this guy is complement is the empty set, right? The union also it will satisfy because union of empty and omega is basically omega, so it's still inside. So this is definitely a field, yeah. But it's a trivial field and not of it doesn't have much of a use. Okay, just it satisfies the definition of a field. Okay. So then okay. So now we are quite comfortable with a notion of a field. We want to extend it to the notion of a sigma field. Sigma, okay. From field to sigma field, because it turns out that the field is actually not, it is not big enough to encompass the kind of space that that contains the usual kind of sets that we might be interested in the study of probability. Okay, so what is a sigma field? So sigma field basically is just a field with some kind of modification to condition 3. So condition 3 is modified to countable unions. Countable unions of sets. Okay. So which means if you have A1, A2, and so on, yeah, there are infinitely many sets, yeah? There can be infinitely many, but they are countable because you have 1 can map to 1 in the, so this is a set of natural numbers, 2, 3, and so on, right? So it's countable, yeah? So if you have a countable number of elements of F, it implies that their union, yeah, is also in F, okay? Implies that if you keep on taking union infinitely, all right, it's still inside F. You contrast it with the definition of field. The definition of field will stop at finite. It just stops at the finite. Sorry, this is N. Finite union, yeah. But for the sigma field, it is extended to countable union. Okay, so that's the only difference, right? The rest of the things are the same. Countable union is equivalently implies countable intersections. Okay, it's the same situation where this actually you have A1, A2 in F also implies that the intersection, countable intersection is in F. Okay. So a sigma field is what we are going to focus on later for the study. But it basically comes from the field. Okay. And then finally, we'll close off with an example whereby our omega is actually not discrete, right? So for when omega is discrete, things are easy. But it can also be an interval, yeah? So we look at example 4.0.3 omega, right? It's actually an interval. So how do we make a field out of this? So we can make a field out of this by considering disjoint subintervals of omega, right? So basically, so your disjoint subintervals will be of this form. AI, BI, right? Open, close. So you can construct as many as you want. Okay, they are all disjoint, meaning that they don't intersect each other, right? The simplest way to sketch this will be like this. This is 0, this is 1, right? So for example, you can have, say, something like this. They can be of different sizes, right? So this is an example, right? This is an example where this is A1, B1, A2, B2, A3, B3, A4, B4, A5, B5, okay? You can basically, it's basically just cutting your line, your 0, 1 line to disjoint subintervals, yeah? And you can form a field, all right, by as follows. You can form a field by including the empty set and omega together. All right. And here is basically a collection of subsets of disjoint intervals. But you have to make sure that this collection here, they will satisfy the property of a field. All right. So I give you an example for you to verify. So here's the example. 0, 1/4, 1/4, 3/4, 3/4, 1, 0, 3/4, 1/4 to 1. Union is and omega. Okay. Sorry, I actually left out the empty set, so there should be an empty set there, right? Just take note, because otherwise, it's not a field, yeah, because it's the complement of omega is not inside the field. Okay. So property 1. Actually, this one you can basically visualize it very easily, right? So this is 0, 1. So basically, you have 0 to 1/4 is here. 1/4 to 3/4 is here. And 3/4 to 1/4 is here, right? These 3 pieces, okay? So property 1 is okay, right? Because omega is inside B. Let's check property 2. Property 2 means its complement must also stay inside, right? So let's check. So this is okay. Complement of empty set is omega. Complement of 0, 1, 4, yeah? Complement of 0, 1, 4 will be 1, 4 to 1, yeah? So you have this one, its complement will be this one, right? Not including, yeah? You'll see this is including 1/4, but this is not including. Okay, so this is definitely the complement. So you have its complement, right? Found already. 1/4 to 3/4 is this guy, right? So its complement will be this guy, right? 1/4 to 3/4 its complement is these 2 parts taken together, union, right? So we'll complement this part, right? So you have the partner here. 3/4 to 1 is this guy here, right? So it will complement with 0 to 3/4. So this guy and this guy complement, okay? So you found all the complements. So A in B implies that complement is there. So okay. Property 3, A, B in in fact, here you have 3. Well, you have multiple. So A1, A2, AN in B implies that the is also in B not, right? So let's check, right? So let me just erase this. Maybe I draw something else. Okay, so you have if you have 0, 1, 4, you union okay. 014 is this line, this interval here, right? If you union 1, 4, and 3 to 3/4, you union this guy, you will get this guy, right? Which is 0 to 3/4, okay? You get this guy. If you take 014, you union so if you take this, you union this, you will get this guy, okay? You take this and union this, you will take 014 to 3/4 014 to, so okay, let me see. So this guy, you union this guy, right? So you will get this guy, right? Okay. So if you take this guy, union this guy, you basically will, since this 0 3/4 is basically larger than it, so if you take union, you basically just see this one. If you take union of this one, so it's 0 to 1/4, 1/4 to 1, so you take union, it becomes omega. So this one is, so you take union, is this one also becomes, this is a larger set, right? So the first round is okay. The second round, you look at this guy and take a union with this, okay? So you take union with this, you can check that it is equal to this one. This one, you take union with this, okay? You will find that this is equal to, so 1/4 to 3/4 is here. You union it with 0 to 3/4. So it basically will be the larger one, right? Okay, so you can basically go through the whole checking. So you have pairwise union, and you also have a union of the tree. So basically a union of the any three elements will also be the same, right? Like for example, you take this guy, union this guy, and union this guy. Okay, you will find that it will still stay in this space. Okay, and in fact, if you union everything here, you should find that they are still staying in the same space. Okay. All right. So this is actually a property of disjoint collection of disjoint subintervals. Yeah. Okay. So we verify that this is actually a field. In fact, this is just for illustration. In general, that in general, this set here can be very large. Depending on how finely you cut these intervals, right? If you cut it like very small intervals, right? Definitely, you will have to have a lot of combinations of unions, right? Later, so that they will satisfy these properties. Okay. So the point is that you can actually generate a field even when your omega is actually a continuous interval, yeah? It's not necessarily just a discrete space. Okay? Right, okay, so I think we will stop here for today. Enough abstract stuff for today, yeah? So on Thursday, I want to maybe use the both hours to do the tutorial.